Hello everyone. In the past video, we have been talking about the pipeline hazards and different types of hazards for pipeline processor. So we have finished the data hazards, and we also introduced the branch hazards or control hazards and how to evaluate the pipeline speed and the stores generated by the branching hazards. So in this video, we will finish the branching hazards and then do a couple more examples about how to calculate the performance of a pipeline processor. So you will have this kind of problem in your midterm exam as well. So it is super, super important, as I said last time. So I put a 5-star in this page, just try to tell you. So for both data hazards and pipeline and branching hazards, for both uh, branching hazards and data hazards. So you will have those problems in your midterm and final exam, in the midterm and the final exam. So I put 5-star again here as well. And we'll look at a couple more examples in this video. So a quick review. Last time we analyzed the branch penalty for a pipeline processor. So what does that mean in general? Then if you stall your pipeline for a little bit time, then this is of course kind of like the extra delay caused by the branching instructions. So because it's super hard for the pipeline to work on full speed, if you do have branching instructions, so you have to do a certain prediction, then what is the next instruction being executed after the branching instruction. And if you do have a prediction, then you do have correct prediction, you do have wrong prediction, right? So anyway, you will have sometimes predict something wrong. And if you predict something wrong, then the whole pipeline has to be stalled for a little bit time to redo everything you have done in advance. And then we call this as how long we have to stall the how long we have to stall the pipeline. This is called the branch penalty. This is called the branch penalty, right? And then the given equation is if the branch can be resolved in the nth stage, then the penalty will be n-1 clock cycles. The penalty will be n-1 clock cycles. Okay, so this problem is required. This is required for your midterm and your final exam. So this is really important. So we will do a couple more examples, and we'll look at a little bit more advanced branch prediction technique for this video. So if we want to predict which instruction will get executed, after the branching instruction, if you can always predict which instruction will be executed, then your pipeline your pipeline can always run in a full speed, right? So if you can always know which instruction will get executed after my current branching instruction, then we don't really have any problem. We don't actually need to stall the pipeline, delay the pipeline for any time. However, this is really, really hard. It's a super challenging problem for modern computer design. So there are some basic technique and some advanced technique we want to introduce. So first of all, the most popular and easiest way to do a branch prediction is always predict the branch is taken or not taken, right? So that's what we have introduced the last time. So you could always assume the branch is not taken, for example. So we always assume the branch is not taken, and then we only need to pay the penalty when the prediction is wrong. So this really depends on how often you have the branch taken, right? How often you have the branch taken. So if your branch is not taken that often, so for certain application and for certain type of programs, applications, there are not a lot of branches anyway. So then you can always use this simple technique to do the simple prediction. The branch is not taken all the time. So then you only need to pay the penalty when the branch is taken. You only need to pay the penalty when the branch is taken. So that's the easiest type of branch prediction. And of course, people will will want to do some more advanced prediction. People will want to do some more advanced prediction. So then we call them, as a lot of them, as dynamic branch prediction. So what does the dynamic mean? It actually means you are changing your prediction when the program is being executed. So the processor is actually changing the prediction. It's actually updating the prediction result when the program is being executed. Of course, it's not always good to do a simple prediction as always say yes or always say no, right? So we want to predict more intelligently. We want to predict more intelligently, right? And if we could do a better prediction and always execute the next instruction with a higher probability being executed, then you want to stack the instructions into your pipeline with the higher probability, being executed. Then of course we could get higher efficiency for the pipeline and whole pipeline. So we have introduced the branch penalty, the concept of branch penalty last time. So this is the number of the clock cycles the pipeline has to be stalled when the prediction is wrong. Remember that you do not always pay this penalty. You only pay this penalty when your prediction is wrong. Right? So it really depends on, how good is your prediction, is, right? So if we always predict the correct thing, then we don't, even we have the branch penalty equals 100 clock cycles, I don't really care, because I will only pay that for a really low probability. So there's basically two things related with the whole pipeline process efficiency for handling the control hazards or the branching hazards. So one part is how good is your prediction? Yeah, right. How good the prediction is. What's the accuracy of the prediction? And the second part is how big is the penalty? So suppose your prediction is wrong, then how many extra clock cycles we have to pay for that, right? So there's basically two parts to determine how well the pipeline processor is designed to handle the control hazards. So what is dynamic branch prediction? Of course, this is a little bit better, a more intelligent branch prediction approach compared with simply predict the branch is taken or not taken. So we could change our prediction along the timeline when we try to when the processor executes the different program, then the prediction result could be changed. And if your prediction result can be changed, then you have to have somewhere to store the prediction result, right? So it has to be inside of the hardware, certain part inside of the hardware. So we need kind of like a buffer, a piece of hardware for us to implement that, right? So we need a buffer or a small memory to indicate if the branch is taken or not. So that's our prediction result. And then the CPU only need to look at the prediction result and select proper instructions to pad them into the pipeline, right? So the CPU takes the prediction result from the prediction buffer and then use it to load the different instructions, and pad it into the pipeline. And of course, if it is a prediction, then it could be correct, it could be wrong. And if you predict something wrong, then you have to redo a lot of instructions, right? You have to refetch the correct instruction, and that's the time when we pay the branch penalty. When we pay the branch penalty. So let's look at a simple example. The easiest type of dynamic branch prediction is called a one-bit prediction scheme. So what does it mean? So for example, so inside of the host processor, so we could have like one small buffer, and one small buffer here is used for the branch prediction. So it's the branch prediction buffer, and it is only 1 bit. Size. The size of it is only 1 bit. So using a 1 bit small tiny memory, then we could put our prediction result into the 1 bit memory. And if it is a prediction result, then there's only two different types of situation. One is you are predicting the branch will be taken. One is you are predicting the branch is not taken, right? The branch is not taken. So what does that mean? So the CPU, the control unit look at this small buffer, and determines which instruction should I pass into my pipeline, right? Which instruction should I pass into my pipeline? So for example, if my current instruction is a branching instruction, and the next instruction is a big question, so which one should I just copy the next instruction next to the branching instruction, or should I copy another instruction which is far away? So which one should I copy depends on the buffer. So each time when we try to pad the instruction into the pipeline, then we look at the branch prediction buffer. And if it is true, then I will pad the next instruction according to the branching label. If it is not true, that means the branch is not taken, then I will pad the instruction which next to the branch instruction, right? So the branch prediction buffer contains a binary value to indicate the branch is predicted to be taken or not taken. So the TNT here means taken, not taken. And then the real example will be a high-level code. You may have in your assembly code, then you may have a branching instruction, and then the branching instruction always has a label, right? And if the branch is taken, then means the instruction get executed after the BEQ will be this one, follow the loop, following the label loop. If the branch is not taken, so suppose I call this AS1, and this is AS2, 3, 4, 5. So suppose the branch is not taken, then the next instruction get executed will be IS5, It will be the instruction after the BEQ. Right? So which one should I put here? So either I need to put IS1 or I need to put IS5, right? So which one I should put on the into the pipeline after the branching instruction? So there's two options. One is IS1, one is IS5. According to my prediction result, is the branch taken or not? Right? So hope everybody understands this figure. So this is really important. All right. So then if I use one single bit prediction buffer, then what value should I put into that buffer? Well, this is a question you may already thought of. So initially, you can put whatever you want, right? For example, I can just temporarily initialize the buffer to be 0, means the branch is not taken. And then if my prediction is wrong, then I have to pay certain penalty to spend extra time to refetch the correct instruction. And at the same time, if your prediction is wrong, then you would like to update your buffer. Right? So if the branch is taken in reality and you predicted it your prediction is not taken, then of course you want to update your prediction. And then you will change your NT to be T. So you will change 0 to be 1, switch, update your buffer, update your buffer. And after you updated your buffer, then maybe next time your prediction is correct. And in reality, like when you have a for loop or like a piece of program get executed for 100 times, a million times, right? So you always have most of the a lot of the time, then your prediction could be correct. So you might be wrong for a couple of times, but you might be correct for a lot of a longer time. So for example, if I have a for loop and I'm looping for 1,000 times, I'm looping for 1,000 times, right? So initially my prediction is the branch is not taken, and my prediction is wrong, so I need to update my buffer when the first time my prediction is taken. And then after that, I don't need to update the buffer for another 999 times, because when I execute the for loop, a lot of the time the branch, if the branch is taken, it will be taken for many times. If the branch is not taken, it might be not taken for many times. So then you don't have to update your buffer many times. And you might have a lot of time your buffer is doing a correct prediction, So, but a question will be, is there any shortcoming? Is there any disadvantage for this kind of scheme? Of course, yes, right? So you are not always correct. If your prediction is wrong, then we would like to know how bad it could be, right? So it's kind of like I put a buffer, and I can keep updating my buffer. So my buffer could be originally T, and then it could be T for many times, and I was correct. And then one day I found, oh, my prediction is wrong. So then I need to redo my prediction, update my T to be NT at that time, right? And then if your prediction is NT, luckily, if you're lucky, then you probably will have your correct prediction for a little bit time. But if you're not lucky, maybe you're doing a wrong prediction again, and you have to update your NT to be T. And maybe you're super unfortunate, and this is wrong again, and you have to update your T to be NT again. So if you keep doing the worst case will be you keep updating your buffer, and you never get a correct prediction, right? So of course, we don't want that to happen, but that could happen, of course, right? So like if you're doing a if-else condition, and then your input to the if-else condition keep changing all the time, and then you kind of like switch your prediction back and forward, and you never get the correct result. So the most popular case could be, suppose we are doing a for loop, and we want to loop this with index. The index variable increase from 0 to 10. So from 0 to 9, 10 different numbers. So the for loop body will be executed for 10 times. So the for loop body is executed for 10 times here. However, this piece of program can be a sub-function, which get executed, get called by a main function. So it could be called by some other function, right? And for example, this function can be called by 1,000 times. And this is in general pretty common. So what does that mean? So each time when you execute the sub-function, your for loop body get executed for 10 times. However, the whole function can be executed for 1,000 times. And in general, how many times you execute x equals x plus 1, it may be 1,000 times 10. 1,000 times 10, multiply 10. I hope everybody gets this, okay? So it is not only executing x equals x plus 1 for 10 times. So if this is a for loop inside of a function, and that function can be executed for many times, right? So you keep executing the same thing. This is really common in any real application. For example, if you're doing a Fourier transform and you're using your cell phone, so your cell phone has like a DSP, digital signal processing chip, or whatever hardware piece, a CPU, and then that piece of hardware keep doing the similar calculation for millions of times every day. If you're texting each other using some communication algorithm, implementing some communication algorithm in hardware, and then the similar calculation like a Fourier transform, like a for loop, like this one, can be executed for millions of times. So suppose that we're doing the real application, just execute the for loop for 1,000 times this for loop, and each time you have 10 times of the loop body, 10 times execute 10 times of the loop body. So my original branch prediction buffer is initialized as T. So my original branch buffer, so this is like the buffer content. Okay, so this is the buffer content. Initialized as taken. So suppose I say the branch is taken on my first time. It doesn't really matter. So what you predict for the first time, okay? So and then the first time, so this is the real case. This is the sorry. This is the buffer. This is the buffer. So this is the branch buffer content, and then the first row is actually the truth. So in reality, if the branch is taken or not, So in reality, the branch should be taken for 9 times, and the last time the branch is not taken because your for loop get finished. Your for loop gets finished. But the first, each row here in the following table, then each row indicate, well, when you execute this piece of program for 1 time, but you may need to execute this piece of program for many times, right? You may have to execute this piece of program for many times. So suppose you have the, so you might have like 1,000 times 10 rows here in the real execution, So how your buffer is updated, So initially your buffer has in a prediction. Initially your buffer predicts the branch is taken. The branch is taken, right? And then we did the correct prediction because the branch is taken. The branch should be taken. So I did a correct prediction again. I will keep that until, well, the last time of the for loop, when I equals 9, when I equals 10, then the branch should be not taken. The branch is not taken. But according to my buffer, it was a T before, so I should have a T right now. So the T is actually, the old value of your buffer. So each time when you try to execute, pad the instruction into the pipeline, then you look at the buffer. When you look at the buffer tells you the branch is taken. So you have the T inside of your buffer. But that is actually wrong. So I'll have to highlight this. So we have a T in a buffer. So we padded a wrong instruction into the pipeline. And then what we have to pay is the branch penalty. You have to refetch certain instructions and redo a lot of things. So you have to pay the branch penalty. So this last row here is a wrong prediction. And after you got a wrong prediction, of course, you want to update your prediction, right? You don't want, so as you already know, the branch prediction is wrong. So I want to update my buffer. Then that's why the buffer value is actually changed to be, the buffer value is actually changed to be NT. It's actually changed to be NT. So I have a N here. I have an N here. Because I did a wrong prediction, so I just changed it to NT. Change it to NT. However, after you finish the 10th row, the 10th column here, you did a wrong prediction, you update your buffer to be N, and then you use N as your prediction when the next time you run this piece of program. However, the next time you run this piece of program, remember this piece of program can be executed for 1,000 times. And the second time you execute this piece of program, your initial prediction is NT, and that is not correct. That is not correct, right? Because the first time inside of your for loop is actually T, but this is the second time you run this piece of program, remember. So you did an N prediction, and that is a wrong prediction. That is a wrong prediction. So what you will do is, well, you have to pay certain penalty. You have to pay certain penalty. And then you update your buffer to be T again, And luckily you get a correct prediction, and you will be correct until the last row, So you were doing a T because previously the prediction was T. However, this will be wrong again. As we know, this is the last row of the for loop. So the last time of the for loop. So you'll be wrong again. And then you update your prediction to be N. However, unfortunately, you will get wrong again because the next time you run this piece of program, you start with a T. You should start with a T. However, your buffer tells you that's a N. So you will have a wrong prediction again. And then you will keep getting correct prediction, correct, until the last column. So in general, so when you have the this piece of program get executed for 1,000 times, remember there's 1,000 rows. There's 1,000 rows, right? Like this. So then, in general, we have about 80% of my prediction is actually correct, and then 20% of the correction are actually wrong. 20% of the prediction are actually wrong, right? So that's easy to understand. So how to improve this? If I'm doing a one single bit prediction, so I have a 1 bit buffer to store the prediction, and I keep updating my prediction result whenever I get a wrong prediction, right? So the worst case will be, you could be wrong all the time. So you change back and forward and you never get it correct, right? So maybe it's better to think about, well, we do not want to change our prediction until I'm quite sure about the change. So, or another way to think about this could be, well, maybe you don't want to change your prediction until you see yourself has been wrong for many times. Or let's say, please be a little bit lazy to change your prediction. Don't respond immediately. It's kind of like interesting thing is kind of like when you determine to buy more stock or Bitcoin. Some of you do some certain investment, so you might consider to buy more or sell more, right? And then sometimes you want to buy more, you do not do your make your decision immediately. You want to watch the market for a couple of days or a couple more hours before you make your decision, right? So just to be a little bit more careful. So a famous approach scheme is called the 2-bit prediction. Right? So the key idea is you don't want to change your prediction until you got wrong for twice. You don't want to change your prediction until you got wrong for twice. And suppose my current prediction is the branch is taken. So my current prediction is T, And then if the branch is taken, then I don't need to change. I don't need to change because that tells me you are doing a correct prediction, right? If the prediction is empty, if the reality is empty, that means you did a wrong prediction. So you are wrong for one time, right? You're wrong for one time. However, I know I made a mistake, but that doesn't matter. Maybe in long term, it's okay. So I will keep predict T again. Until I know I made a mistake again. So if the prediction is not taken for another time after that. So I made a mistake for twice. So I made two mistakes next to each other. So that tells me don't be wrong again. You have been wrong for twice. And that's the only time I will switch. So I will update my prediction to be NT. And suppose I'm currently predicting NT and the reality is NT. If the reality is NT, then I do not need to make any change. However, I might be wrong for certain probability. I may be wrong, right? So if the reality is T, so I will write the reality in the blue color. Yeah. If the reality is T, so what happened in the reality is, well, when the program get executed, you made a wrong prediction. So you are predicting NT, however, it should be T. So that actually means we did it wrong. So the prediction was wrong for one time. And it doesn't matter. I will still keep my prediction to be NT. I'll still keep the prediction to be NT until I get, unless the next situation is also T. Unless the next branch is also T. That actually means I am wrong for twice. So when I am wrong for twice, then I will switch my NT to be T. I'll switch the buffer. I'll update the prediction buffer from NT to be T. So what does that mean? It actually means just be a little bit lazy to make a change. Don't make a change immediately after you made a mistake. If you keep making mistakes for a couple times, then you can change your prediction, right? So what's the benefit of this? Then I have to, draw 5 star again. I have to tell you, you will definitely see this in your midterm. If you don't see it in your midterm, you will see it in your final exam. So this is super, super important, okay? So if I have a 2-bit prediction scheme, suppose we're still doing the for loop, and then this for loop again will be executed for 100 times or 1,000 times. So each time I execute this, I need to implement the body for 10 times. However, this whole program can be executed for 1,000,000 times, right? So it's 100 times of the following. So the very first time when I execute this piece of program, initially suppose we start with T, so that's how the buffer was initialized. It doesn't really matter, the first initialization, okay? So even the first row, it really doesn't matter because you might have many rows. Right. So suppose the buffer was initialized as the branch is taken. So the prediction was T, and I will keep doing T because I'm doing a correct prediction because I was correct. So I'll keep doing T, right? And the last column is kind of like a little bit tricky. So the branch should be not taken, should be NT. However, according to my buffer, of course, I have a T here because I would just follow what I have in the buffer, right? So what I did is a T, right? What I did is a T. And your prediction is a T, and what is the reality is an NT, so that means you did the wrong prediction. You did the wrong prediction. So that last row here, the last column here is a wrong prediction. That's fine, that's okay, right? Remember, we're using a 2-bit scheme, so I'm not that fast to change my prediction until I see making mistake. I see myself making mistake for twice. So I made a mistake, and I don't really worry. I will keep predict T because I don't want to update. I don't want to update my buffer until I know myself has been wrong for twice. So I have been wrong for once. It doesn't really matter. So I will keep my T prediction, and luckily it is correct. It is correct for the next time when you execute it. It is correct for the next time when you execute the whole program. And then there won't be any other problem in the columns in the middle until you got to the last row again, the last column again. When you got to the last column, then we have a T according to what we did just now previously, right? Because you have a T here and then you will have T here. So when you have a T in the last row, unfortunately, you get it wrong again. However, because you're lazy to make a change until you see yourself making mistake for twice. So I made one mistake, but it's fine. I will keep my T. So I'll have a T again here. And then you know what's going on. So in general, then you always have T, dot, many rows. And the last row is always T. However, it is always wrong. Right? But compare this with the previous example. So what is the accuracy of the prediction? So you got about 90% correct prediction, and about only 10% prediction are wrong, right? So this is a really important scheme called 2-bit dynamic branch prediction. So I hope all of you understand this example. And then you might ask, how about if you make the prediction scheme even more complex? So that's out of our scope. I can tell you there are studies show that there's no significant improvement if you do an n-bit prediction. So the 2-bit prediction is really common implemented in a lot of systems. All right, so so one more example for you to get you prepared for the midterm exam. How to calculate the CPI for a pipeline processor. So we remember that in this whole slide, we have covered pipeline processor, and I told you the ideal. If I can make a copy of this, so maybe I want to make a little bit more note. So the ideal CPI for a pipeline processor is 1 cycle per instruction, right? It's 1. I should not use unit. So the ideal CPI for a pipeline processor is 1. So watch my previous video if you didn't understand this. If you don't understand this. So the ideal CPI for a pipeline processor is actually 1. So we wish we can use 1 clock cycle to implement each instruction in average, right? So when you're stacking many instructions in your pipeline, then in average you want to have spend only 1 clock cycle for each instruction. So there's no pipeline stall. However, there's a lot of pipeline stalls in the reality. So the stalls are generally caused by 2 reasons. So one is by data hazards, because you do have a lot of data dependency, right, in the instructions. One is called by the branching or control hazards. Branching or control hazard. Right. So then when we calculate the real CPI, the CPI in reality, of course, that equals the ideal CPI plus the extra stalls, we have to pay by for the data hazard, and both the data hazards and the control hazards or branching hazards, right? So how to calculate the real CPI for a pipelined processor? Let's look at some example. And suppose I tell you your given processor, pipeline processor, only have the data hazards or only have the branching hazard, then you should know how to calculate the real CPI for a pipeline processor, right? So suppose we only need to deal with a branching hazard. So there's no data hazards. Inside of the given processor, And then for my branch hazards, then I'm curious about how much extra stall it will generate, right? So if I'm able to calculate how much extra time I have to pay for the branching hazards, then I'm fine to calculate the real CPI for a pipeline processor. However, remember, not all the instructions are the branching instructions, right? Suppose you have 100 instructions, and maybe only 20 of them are branching instructions, right? So, and the 80%, they're like a basic ALU calculation, for example, right? Some other load and store, some other calculations, some other instructions, right? So only the 20% branching instruction could generate branch penalty, And remember that inside of this 20% branching instruction, you do not always have to pay the branch penalty. And what time do you have to pay the branch penalty? When you made a wrong prediction. And this is really important, how accurate your prediction is, right? If we have a correct prediction, then there's zero clock cycle we need to stop. So there's zero stall in the pipeline. And if there is a wrong prediction, then we have to stall the pipeline for n-1 cycles, right? Suppose the branch can be resolved in the n stage, then we have to stall the pipeline for n-1 cycles, right? However, this is not always true. How often it is true depends on your prediction accuracy. Suppose the prediction accuracy is 70%. And then that actually means for 30% of the time, then you need to pay the branch penalty. So suppose this is the real example, then how can I calculate this processor CPI for a pipeline processor? So the pipeline processor need to execute many instructions, and 20% of the instructions are branching instructions. Within the 20% of the branching instruction, I may have a wrong prediction for 30% of the time. And each time I had a wrong prediction, I need to pay n minus 1 extra clock cycles. I need to pay n minus 1 extra clock cycles. And the real CPI for this pipeline processor has to be 1, which is the ideal calculation time, plus the extra penalty I have to pay, when I made a wrong prediction. However, only 20% of the time in average inside of each instruction, 20% of the time you will have it as a branching instruction. And within a branching instruction, you will have 30% of the time you made a wrong prediction. And when you made a wrong prediction, then you have to pay n minus 1 extra clock cycles. And this will be the real CPI for this given pipeline processor. Okay, so this is super important. You will have this in your exam for sure. So please try to understand this example. If you have questions, send me in Teams. All right, so I will stop here, and I will post announcement about the midterm exam soon.